my name is Roy Simpson, and I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another video in my Proofs in Differential Calculus series. In this video, we are going to take on the dreaded product rule. This rule is, I think, a harder proof for students to get, but I will try to present it geometrically so it's a little bit easier. In this theorem states the following, that if you have a couple differentiable functions, then the derivative of the product is the first, well, in this case, f times g prime plus g times f prime. And this goes counter to what a lot of students would hope. A lot of students honestly hope that that f times g, the derivative of it, would equal, which it doesn't, f prime times g prime. There are a couple things that you should know prior to beginning, some prerequisite knowledge. Those two are limits and obviously the limit definition of a derivative, because we're talking derivatives here. You should probably also have a passion for this stuff, because this is going to be one of those proofs that requires such passion. But we'll be able to do it. Before we delve into the proof, I'm going to have to work out some scratch here. We're going to just discuss the ideas of the derivative of the product of two functions. So remember, we are just taking the derivative with respect to x of f times g. And remember, g and f are both functions of x. Well, we know that this is supposed to be the limit as h approaches 0. I was going to put x there, but it's supposed to be h approaches 0 of f times g of x plus h minus f times g of x all over h. That's just the definition of the derivative. Now, for our proof, I'm just going to say this is roughly equal to f times g evaluated at x plus a little wiggle. And a little wiggle we're going to call delta x here, so it's just a little shift in our x values. And then obviously the second one is just f times g of x. And that's all over the little wiggle itself. I was going to write something wrong there again. Okay, there we go. So you can see that this is, hopefully you can see that this is basically the same as the limit. It's just without the limit notation, so this is not exactly the same. This is an approximation. We have in the limit the product of two functions evaluated at x plus an infinitely I can't say that word, a very small infinitesimal value, something very close to 0. Okay, so x plus something incredibly small minus f times g at x. Well, here we're saying the same thing. We have the product of two functions evaluated at x plus something small, but not really 0. It got some size to it, minus f times g of x. So we do have an approximation on the right hand side. And I'm going to introduce some notation, some extra notation. So this bit right here, I'm going to call, let's call that a wiggle in f times g. So that's my wiggle in f times g. Because look, downstairs we're calling that a wiggle in x, so why not call this a wiggle in output? Because it's a difference in outputs, it's just the wiggle in outputs. And what we want to get to, well, with the limit, we want this to be f prime g plus fg prime. But in our wiggle notation, we want to basically say this is kind of, well, if you look at the notation up here, this derivative of f times g is a wiggle in f times g over a wiggle in x. So the derivative of f must be a wiggle in f over a wiggle in x times g plus f times the wiggle in g over a wiggle in x. So these, right, change in f over change in x, that's change in output over change in input, that's a slope, right? So we're just saying that's approximately the derivative at f, or derivative of f. And then change in g over change in x, we're saying that's approximately g prime, right? So that's what we want to get to. How we are going to get to that is, well, a little bit a geometric way. The only way that I could ever remember was geometrically. So if you play along with me a little bit, we're going to go ahead and do the geometric derivation. Normally, when you want to multiply f and g, well, in this case, find the limit, you have f times g in there. So we can think of f times g as being an area. Let's pretend that represents the length f, and this represents the length g. And when I say this, I mean from here to here, and from here to here. Then you can imagine f times g is just this center area, f times g right there. What we want to know really, truly, is how much does f and g change when we wiggle the input? That is, what is delta fg if we wiggle the input? Well, let's go ahead and wiggle the input a little bit. So going down to this bottom function f, if we wiggle the input a little bit, let's just pretend it creates a little change in f. So again, this part right here, and let me go ahead and draw it out with maybe a highlighter. This yellow part right here is what f is. And when we wiggle f, it just adds on just a little bit extra to our wiggle. So maybe like this much extra. And so we get this f plus a little delta f. And we could also wiggle the inputs for g, and so we have this side g. Let me go ahead and highlight it. This side right here, g. Not very much for highlighting because my highlighter's narrow in this direction. And we are going to wiggle it just a little bit, wiggle the input, so that the output for g wiggles a little bit as well. And so you can see that when I wiggle the input, the output wiggled by this much right here. So let's see what happens to the area of this rectangle, which represents the product of our functions. Let's see what happened with the area of this rectangle when we wiggled the input. Well, I see that we added on 3 different areas, not 2, but 3 different areas. Going from the upper left-hand corner, this area right here with the purple edge on it is length f times height delta g. So a little wiggle in g times f. That's the area of that little block. The little block in the corner, the upper right-hand corner, is delta f times delta g. So a little wiggle in f times a little wiggle in g. And something to point out about that right there, that area, you can see that if we wiggle f by less and wiggle g by less, that area is going to be really, really small. And in fact, it contributes very little to our problem in the long run, but we'll prove that. And then finally, the bottom right hand rectangle here is going to be of width delta f and then of height g. So we see that when we wiggle f times g, or when we wiggle the inputs, the output has wiggled by, so the wiggle in the output is going to be these extra squares, or I'm sorry, extra rectangles that we've kind of glued onto this. So it's f times change in g plus change in f times change in g plus change in f times g. So we know that our output has wiggled by this much. Now honestly, this scratch work that I'm doing right here, I probably would use this in my proof. I would honestly kind of draw this geometric figure to allow for somebody to believe my proof a little bit more than me just algebraically writing things down. So with this, let's go ahead and start the proof. So we begin, just like most of our other proofs, with our supposition that we have a couple differentiable functions. Then we'll go ahead and state what the limit of their product should start to look like. And I'll actually write this out longhand at first. So this is the limit as h approaches 0. I'm kind of copying down what I wrote down earlier. The product of f and g at x plus h minus the product of f and g at x all over h. And of course, this, as we wrote down earlier, is the limit as the change in x approaches 0. The denominator is just going to be our change in x, and the numerator will be our change in output. And I might have to kind of justify that for some people, so I'll go ahead and maybe I'll shorten up that fraction bar a little bit too. But I want to justify that by saying, maybe not justify, but just kind of let people know where I'm going with that. So where the change in the product of those two functions is just a shorthand notation for f times g of x plus delta x minus f times g of x. Just in case somebody says, wait a second, you're introducing some stupid notation here, I don't get it. But now we are going to go ahead and refer to the drawing that we just did, and note that the whole change in f times g, which we actually have an algebraic expression for over on the right hand side, which we said, oh, that's just f times g of x plus delta x. Oops, that's supposed to be an x. I'm used to writing delta h's. Minus f times g at x. A way to interpret that is to say, well, I just need to know how much does f times g change when we wiggle the input by delta x. And that's exactly what this question is asking. How much does our output change if we wiggle the input by a delta x? And so that allows us to say that this bit right here, let me highlight it, that this is equivalent to our delta f times g. So that's good enough for us. I mean, not just good enough, that's actually perfect. That's exactly what it is. Now, before I actually walk away from this and go back to the main part of the proof, I want to make sure that people actually understand that we have what everybody else says we have is f times g, and we're just going to wiggle our inputs a little bit. And when we wiggle those inputs, we get this brand new area, all of this stuff. So this is what we get when we wiggle those inputs. And so that green area that I've slashed there is actually the change in f and g. That's what we're going to write down in our proof right now. So that says that that's equal to the limit as delta x goes to 0 of, and I'll put this in a big bracket because it will make my life a little bit easier, change in f times g plus change in f times change in g plus f times change in g, and that's all over the change in x, right? Because our denominator is that change in x. Now, of course, we should kind of talk about these notations, what the change in f's and the change in g's are. So just for completeness, I'm going to write that here as well. And like I said, that's just for completeness, so that somebody says, well, you're introducing a notation I don't quite understand. You can say, no. Change in f means the difference between my wiggled output and the true output. That's all. All right, so let me rewrite this. This is a limit as the change in x gets really, really tiny of, this will be delta f times g over delta x. Notice how I'm writing that denominator. I'm actually writing it right over or right underneath the delta f part. Plus delta f times delta g over delta x. Again, I'm just writing that underneath the delta g part now, not a big deal. Plus f times delta g over delta x. Now we can split all these limits because we were told that the derivative for f and g both exist. So that first part right here, let me go ahead and highlight it. This first part, delta f over delta x, that as the limit as delta x goes to 0 is actually f prime. And the same thing, delta g over delta x, that's g prime as delta x goes to 0. And same thing with this last bit. So this implies that we have the following: f prime of x times the limit as delta x approaches 0 of g plus the limit as delta x approaches 0 of delta f, and I should put that in parentheses, times, and we just said that that one's going to be g prime of x, plus the limit as delta x, it's supposed to be a delta x, approaches 0 of f, I'll put of x here so that I can kind of talk about something in a moment. I'll put that of x right here as well, so I can talk about the same thing there. Times, and of course the limit as delta x approaches 0. That highlighted bit is just g prime of x. Now, this equals something very nice. If you look at this first, and let me highlight it so that we're all on the same idea page. If you look at this first limit here, the limit as delta x approaches 0 of g of x, there's no delta x in there, just a regular old x in there. So that limit, or I'm sorry, that function does not rely upon delta x. It only relies upon x. So that limit will just become g of x. Likewise, at the end, f of x here, and let me highlight that as well, so you can see that, f of x here does not depend upon delta x either. It just depends upon x. So again, the limit as delta x approaches 0 of f of x is just going to be f of x. And this will be times g prime of x. The stuff in the middle is the interesting bit, because we have here times g prime of x in the middle. But what is, and I'll draw this here, what is this? This bit right here. Well, we wrote it up here, and there was a reason why I wrote both of these to kind of maybe guide somebody along in our proof. We wrote that delta f is f of x plus delta x minus f of x. Let me write that in here just so I can convince you of something. This is plus the limit as delta x approaches 0 of f of x plus delta x, sorry it's so small there, minus f of x. As delta x approaches 0, this is going to be f of x minus f of x, which will be 0. So that term right there, again, as delta x approaches 0, that'll turn into f of x minus f of x, which will actually be 0. So that center term will disappear, and we get the final answer, f prime of x, g of x, plus f of x, g prime of x. That is the proof. Pretty interesting proof. And by the way, that center term that's in purple right there, let me just go ahead and show you that in our geometric area here. That is actually, this is going to look really horrible just because I have so many highlights overlapping, but that's this bit right here. This bit actually tends to 0. So that's kind of a neat idea. That bit actually tends to 0 much faster than these other green areas right there. So that bit is just essentially 0 as our change in x gets really small. Alright, so that's the proof of the product rule. Turns out the quotient rule is not so bad, but the product rule, that's the one that's difficult to prove initially.